Это наш коллега и партнер, с которым мы много исследований проводим совместно, в том числе мы деловые игры разрабатываем для рынков электроэнергетики. Соответственно, сейчас он расскажет про один достаточно интересный проект, по которому он потенциально хочет с нами сотрудничать. Ну, единственное, доклад будет на английском языке. Дэвид может нам сказать «привет, пока», но все остальное на английском, как, собственно, принято в Сколтехе. Поэтому...
Это не Сколтех, это Калтех.
Нет, это Сколтех.
Сколтех.
Это да. То есть, на самом деле, Дэвид сотрудник Российского университета. Причем достаточно уже длительное время, но там немножко другие стандарты, чем в других университетах. Вот. И Дэвид расскажет, это совместный проект с MIT, насколько я знаю. Окей, Дэвид, so... And it seems that our schedule changed a bit, so you have any time you'd like, just to see if the audience is still ready to understand.
Good afternoon, everyone. I'm sorry I can't speak Russian. I hope you can understand. Thank you for the invitation, dear colleagues. Thank you for the invitation in the live. It's an honor for me to be here and to explain. I will introduce you a project that we are working right now, which is related with quantifying the value of data in complex systems. This is an ongoing work, so probably I will finish with more questions than answers. But the idea is just to open discussion probably here with all of you. I'm from Skoltech, an assistant professor. I've been here 4 years in Russia, in Moscow. This project actually is a joint project with a team of MIT and with Professor Dalek. Also at Skoltech, we have Professor Janet Bialek. So Professor Janet Bialek is working in the area of energy systems, specifically power systems. Myself also have background on electrical engineering. Also working in power systems. And the idea of this project is just to understand the value of data in the context of electromobility and power systems. So we try to understand how to create markets for data, how to quantify data, and to give the value of the data in a specific context. So there is this is kind of keywords of what is the project about. And the motivation is like we see in the last year that there are many places they are moving from classical internal combustion automobiles to electrical ones. So this is an example of Shenzhen in China. So they replace fully the fleet of buses by electrical buses. This is already about 3 years or more. And we have seen many countries that they are now moving, like Norway, more than, I think this is a bit old, but I think now more than 50% of the new cars that they are purchasing are electrical ones. And this is kind of the trend. This is the typical curve, adoption curve when a new technology appears. So how is this evolution? So in Moscow, you can see now electrical buses as well. So this is kind of a new reality. So we have new actors in power system. There are these electrical vehicles. But what could be the impact of those electrical vehicles in the power grid? So, and it's like medium-sized electrical vehicle can charge at the power of 60 kilowatts. Some of them depends on the type of charger. Some of them can go even 100 kilowatts. But let's put just 60 kilowatts to have an order of magnitude. Then just to have an order of magnitude, a nuclear power plant is about 1 gigawatt. 1.2 gigawatts of power. So we have 10 of those electric vehicles charging at the same time. So we expect to have 600 kilowatts. Or if we have 20,000 electric vehicles charging at the same time, it's more or less equivalent of the power of one nuclear power plant. Obviously, the electric vehicles are charging at the distribution grids, which are not actually prepared for such a big capacity of power. And 1 million of electric vehicles is more or less 15 nuclear power plant capacity. Okay. Just to have an order of magnitude, Just to also understand, in Russia there are about 52 million of automobiles. If 20% of them they are electric vehicles, so this means like this is about 2.5 of total demand, annual total demand, back in energy. And yes, let me jump to commercial automobiles. More or less there are 8 millions, and this is more or less 2% of the total demand. If all of them they are electrical. So just to have another magnitude of the impact of the electromobility sector in Russia, for example. In Moscow, there is on the streets about 3.5 million of electric vehicles. Just 1% of those electric vehicles charging at the same time means that they require 3.5 gigawatts, so more or less the nuclear power plants of power. So the impact, of course, is big. I think this is not new. Everyone knew about that. And there are solutions. They are trying to think about this, what is called a smart charging. Today, everything is smart. We have smartphones, smart fridge, smart homes. Everything is smart. It is called also a smart charging. And the idea of this smart charging or the use of these small batteries for providing some services or to have the control of large number of electric vehicles it's not that futuristic, right? So we see like there are many countries with compromise of forbidding fully the new electric vehicles. There are, for example, California also they are writing new rules for the possibility of providing services. What is called able to grid charging. So you have to own electric vehicles, and it is possible to provide services to the grid. Of course, we have to think about how to provide the services to the grid. There are plans in many places. Some practical issues is, for example, last year, Tesla, the company, launched what is called Autometer, which is a service that can make use of the static batteries. It's not for electric vehicle, but just if you have a power wall, there's a battery in your home, you can use this battery for providing services to the grid and get benefit from that. So the Autometer basically is a software which is running that says when to do trading with the electricity markets. This is possible in many countries because there is legislation, there are rules that allow that. Of course, in many other countries, it's not possible because they are not that good. For example, Australia you can do. In Europe, also they started last year to do it as well. So still, they are not using electric vehicles for providing this service, but could happen like in near future. All the electric vehicles from Tesla can provide service to the grid. And service can be what is called frequency regulation, voltage control, demand shifting. So there are different types of services. So what are the type of smart charging? What we call a smart charging. So the smart charging can be in a different levels. So the simple one is like I provide you an incentive. So I give you a tariff. So at the night, the price of charging an electric vehicle is lower than during the peak hours. And this is an incentive, and this will in somehow impact in the way that the charging is done. So this is the kind of the very simple implementation that we can have. But we can make a more sophisticated way of smart charging or control. So we can have on-off control. We can have just not on-off, but also how much power we are charging at a specific moment. This is kind of people want to grid just in one direction. We can have bidirectional control with the energy that we have in the batteries can be used for providing services to the grid. It's just not from the grid to the vehicle. And something more sophisticated like with dynamic pricing, for example. What we are proposing in this project, so this is not new. I mean, like this is just a summary of what people have been thinking about for several years. What is new here is like we want to use also data. So because for doing something smart grid are smart because there are plenty of data.
smart fridge are smart because they have a lot of sensors. Everything is what we call smart is because there is plenty of data. So what we want to do here is to understand the data that is generated from electric vehicles, how useful can be for the grid operator. Okay, and this is the last part that we try to work with. We are going in baby steps, but we started to do some data. Okay, so data has value if there is uncertainty about something. So if we don't have uncertainty, new data maybe doesn't provide too much value. So data usually is coming with uncertainty, or the value of data coming with uncertainty. And also it's important to understand what is the contextual use. So yes, I like this picture. You cannot see it very well, but basically it's a bookstore in China. So everything here is in Chinese, but they are selling books by weight. So they say like 1 kilo of this type of books is 8 yuan, and the other 1 kilo for other type of books are in that. So this looks like very crazy, buying books by weight. But currently data is like this. So we are buying data by terabytes or by gigabytes. So this is, or we pay a subscription to Bloomberg. Every month we pay, and then we have data about stock markets. We have data about what is the forecast of some technologies, whatever. So this is the way that now data is sold. Probably there is some reason why. So the first thing, why we cannot create markets for data? Like we have market for vehicles, we have market for energy, we have market for apples, but we cannot create market for data. And there are some specific challenges that make data a bit more complicated to manage. That we cannot just replicate the rules and the properties of other markets in data markets. Okay. So the first one is we can replicate data at zero marginal cost. What does it mean? We can make a copy of the data, and now we have the same data we have twice. We cannot make a copy of an apple, and we cannot make a copy of the energy. So if we want to produce more energy, we have to some marginal cost for producing that. So marginal cost of the data in principle is zero. The value of the data actually is very intrinsic to its use to the company. So for example, like what is the data that Yandex Map is providing actually can be very useful for a taxi driver. But maybe for me right now, it doesn't have any use. So the value of data is very intrinsic. And in principle, yes, can be combinatorial. I will come back later to this. The value of data also is connected with the task that we want to use. This is kind of almost the same thing. So if yeah, so I will come back later. So I think about this is very intrinsic to the use, to the context. It's very difficult to give a value to the data if we don't have the data. So if I go to a product shop and I see some apples, I like those apples, I can buy this apple. I know the price, I know those are the apples, and they looks very good. So I can buy those apples and I'm okay. But data is not like this. So for understanding what is the value of data, many times you need to have this data to see if it has some value. Think about linear regression. So if you want to do some regression analysis, until you don't have your data, you don't know how good will be the regression. Yeah? So this is a very complicated part of creating market data. And the last one is related with externalities. So if there is several companies, they want to purchase data, and if this data is already sold for one company, and then the other company may think about if the value is the same as if it is not with the first company. So in other words, so the data can create some competitive advantage for some particular companies. So if you already sell to this company, maybe the second company will not find that value because this company knows the secrets, so they know what will be the demand for this particular product in the next year. So this is kind of related with externality. So this value actually creates some externalities in other companies. Okay, so this is why there are some challenges. The first question that we try to answer is before creating markets. So how we can quantify data? So can we make a quantification of the data? And thinking about quantification, we come up with three main pillars that we need to consider for quantifying data. The first one is the contextual problem. So where we are using this data. The same data may have a lot of value in some particular problem, some particular context, but may have no value in other contexts, like let's say just map. The metric of performance, how we are going to measure, what is the metric that we want to use. And then the third one is the allocation, how we are going to allocate the value created through all the participants for providing this data. Okay, I will come back one page for each of them. I will say with one example. So this is very simple example how we can quantify data. So let's imagine that we have some data. We do some regression analysis. For example, what are the sales depending on the budget. Okay, so let's say this is linear. When we have this type of linear regression, in somehow we can understand the importance of particular features with respect to the accuracy. Like if those beta, those parameters are very close to zero, it means they probably are less important than the other ones. So somehow we have a rank for understanding how important is a particular feature. In this case, the context is a regression estimation. The metric will be accuracy, and the allocation rule can be organized, ranking those betas. Okay. This quantification of the value is not new and have been a lot of work in the last 5 years in the field of machine learning. So machine learning is now a hot topic in many places, but at the same time, those machine learning models are say that they are black box. We don't know they are working, and we don't know why they work, but they are a black box. So there have been a big effort to understand or to interpret why they are working. So and then they have come a lot of papers and ideas of quantifying. In this case, quantifying features of any particular model in something that can explain. Like for example, I don't remember what is the sample, but let's say this is related with some illness. And now you see here like age, sex, this is body mass index. So you can see here how important can be each of those elements. So basically they are using here Shapley value from comparative game theory. And this is a way of doing that. So in the context of machine learning, we can find this idea of quantification of data, of the value of data, but it's coming in a different keywords like interpretability, explainability of these models. Okay, so there are different types of data. So we can use from historical values to some forecast in some particular context, even some data which can be online. And here I want to make the first important observation. We can use features as typically have been done in these machine learning applications to understand which features. Is the age important? How important is the age? Is the body mass index important? And how important is this? Or we can use data points. Sometimes it's called samples, observations, depends how it's coming this data. But an observation is basically, a data point is just an entrance in these big macros. So in this case, in our context, we are focusing on these data points to understand like every electric vehicle, every individual can actually provide information to a big and complex system, which is a power system, for improving the operation. So we want to use new data for the context of power system, and we want to quantify the value for every data point. Okay. Any questions so far? No?
So, David, finally, the main idea is that electric vehicle or customer is a data point. Yeah? So
a customer is a data point, yes. In our case, I will give you the context where we are going to use is a charging event. So when the user is arriving, so arrive to the office at 9 in the morning, the electric vehicle will be connected all the time until he's leaving. And during all this time, it's possible to charge. So this is kind of event of this. But you can see like only a user, a customer, sometimes we can call player, because you will see this is connected with cooperative game here. Okay, so let me explain you what is the context that we start to apply this. So our context is the power grids. It's kind of my background, an electrical engineer. And this is representing a distribution grid. So the idea is that let's assume that we have EV charging station. It's just not one electric vehicle, but it's a charging station that have connection at different places, different location on the grid. And the grid operator need to operate the system in such a way that minimize costs and minimize losses, for example. So the grid operator doesn't have information of the true demand of those electric vehicles, but have some tools that can help to forecast what will be the load of this EV charging station. Right? The same for here, the same for here. Okay. So what is the context? So we try to mimic, to replicate what is implemented right now in most of the power systems. So this is this two settlement stage. So in the day D-1, one day before, there is a dispatch of the energy. So we decide how much energy we should get from the main grid. If we have local generators, how much we should produce, etc. Then there is a commitment for that. And then in the day B, at the moment of delivering the energy, we observe what is the true demand. We have to balance. So if we purchase more energy than we need, so we have to reduce. So we have to balance in negative. Or if we have less energy than we need, so we have to buy this in the real time. So then in the day ahead market, just before it's happening the delivery, there is uncertainty about what will be the true demand of electric vehicles. So the only thing that we can use is the best forecast that we have at this moment. Okay? This is a deterministic approach because we are using just a forecast point. Okay? We are not using any. We can make a more sophisticated model for the day ahead, but this is what is typically implemented in the power grids. Okay, so we just mimic that. This is again, this is the same. So we have a model that forecasts the EV loads. It's coming as an input for the deterministic day ahead market. There is this commitment for generation and for purchasing energy from the main grid. Then we have an observation, what is the true real EV demand. So, and then we have to balance. We have cost in the day ahead, so what we call here day ahead dispatch cost, and there are costs in the real time. So this is the total cost for the full operation of these two steps. So I assume like the grid operator is the value. So this grid operator wants to buy data. So we have only one buyer of this data. Want to buy data from EV charging station, electric vehicle charging station. Okay, so we have in this case the very simple one. Yes.
What's the dispatch cost?
This is the day ahead. The day ahead. So the dispatch cost is like the commitments for the generator. So tomorrow this generator should produce this amount of energy, and this is already a commitment for the next day. This is how much we have to pay up to this generation. Yeah. And because we are also at this is in the case of a high voltage level, at the low voltage level distribution grids. So we can purchase this from the main grid, from the high voltage through the substation. So here is, I haven't said, but this is the connection to the main grid, to the substation. I will show you an example here. Typically, this is cheaper than producing locally. Okay, this is kind of the very simple setup. This is a playground. We just mimic. We make a replica of what is the market, and we just these are classical optimization models in there. So then we assume that we can have one seller. In this case, we may have more than one, but we started with a simple thing. We have one seller, which is a data aggregator. So this data aggregator is in charge of collecting data from different EVs and selling to the grid operator. Okay, so this is done through some marketplace. So different EVs aggregators can share data, and for now, this is something that we're still investigating. We assume that this data is true data. So I say like I will be with my car tomorrow here in the IPU at 9, and this is true. So of course there is uncertainty because I may come here at 9:30. So there is a lot of uncertainty. So for now we assume that this is a true data. We are still thinking about how to extend this idea for something which can be stochastic. Okay, so this data, because it's true, will in principle improve the overall operation of this system. Right? These two steps ZFN. It should improve because this forecast is not perfect. It's coming from the model of the grid operator. Okay, how we close the loop? So all this data from all these electric vehicle charging stations provide some additional value, and this value will be closed in the loop. So let me put like this. This is how we close the loop. This total cost can be reduced. This total cost can be reduced, and this avoided cost can be used for compensating those EV charging stations. Different type of business model can be also possible, but this is a kind of the business model. So we can see here we have generated value in principle. We can generate value from this data to a complex system, and this value is based on avoided cost, how much we are going to save. So this can be actually allocated among all the EV charging stations. Okay, so this is our contest. So the metric that I want to use, I already give you a tip, is the avoided cost. And this is related with the business value. Here is an important difference that we are making from this machine learning community, because all these machine learning models are very focused on forecasting something. And probably you know about this Netflix competition, was probably 5 years ago or 6 years ago, that there was a competition to understand. It is the problem called matrix completion, but basically just to forecast if a new user is coming to Netflix, what will be the favorite movies of this guy. And they, at this moment, also they understood like probably the best forecast doesn't mean the best business value. And in general, both things can be different. I will show you if this is the case for our samples. So mean square error, like one of the metrics that we can use for seeing how much we have improved our forecast. is not exactly what is the avoided cost. Okay, so we use a value of this avoided cost as or best business value. Yeah, B is coming from, this is the value which is generated as avoided cost. How much we have saved in the operation of the system because we have new data for available to the operation of the system. So this delta B is as extra profit. Yes, we can say like an extra profit. It's a value that is generated, and this value can be quantified how much we have saved from using data that we don't have before. Okay, and this is closing the loop. I will sometimes call B like typically this symbol is typically used in cooperative game theory for the value function, and I'm using this capital N representing all the guys that are providing data. Okay, so I'll come back later. Okay, so yes, so here is our playground. So this is these two things. So the next thing is to understand, well, if we have some extra profit, how we can share among all the individuals they already provide data. And here is the next part, how we can allocate value among different players or different EV charging stations. Of course, this is very classical thing for cooperative game theory. So we have a value, and we see like this looks like a cooperative game. We just need to think what is the best allocation rule for sharing value. There have been done a lot of things about using Shapley value. Shapley value is the gold standard in many aspects, and this is kind of what is called. Well, this book is very nice from William Thompson. So he say like there are three different ways of attacking this type of approach. The first one is direct approach. We select what is the allocation rule, a rule for sharing. We can do equal sharing, and that's all that. And then we go. We can look in the axiomatic approach that we decide what are the properties that we would like to have as an allocation rule. What the properties are nice. And the other one is a bit more sophisticated. It's we call game theory approach, but everything is game theory. But he mentioned that we can include some forbidden interaction or some preferable interactions, etc. So we go here in the axiomatic approach is just to define what are the properties that we would like to have when we allocate value of the data. Okay. And I have these two-stream things, properties of allocation rule. There are many of those properties, but some of the properties try to look what is the marginal contribution for individuals to a particular game. And at this very extreme, probably we can find the Shapley value. And then there is the other extreme, like say, well, everyone is equal, so let's divide the total value equal in equal shares. So equal division rule, and it's okay. It's like if we go for a dinner, we have a nice dinner, so let's divide the bill in the same. Of course, so you can see like many of the problems, even contemporary problems, are neither using marginalist paradigm or egalitarian paradigm. For example, you can think COVID vaccination in many countries. So there are, in principle, everyone is equal to access to vaccination, but when there is a scarce resource, they start to provide COVID vaccine for risk groups. Right? This is typically done in many places, like in Europe. So it's not either egalitarian, but neither marginalist. So which group will get the larger marginal value of this COVID vaccination? So here are the properties that we believe they are important for allocating value of data. The first one is efficiency. It is called, in other contexts, it's called budget balance. So it means like all the value generated is fully distributed. There is not money left. There is not money missing. The second one is symmetry. So there is no discrimination. If you provide a particular value in a contest, so you should receive the same value, monetary value, right? So there is no discrimination. The third one is linearity. This is coming with the idea of using superposition. The fourth one is a null player. So if we have a player, or if we have a EV charging station that is providing data, but this data doesn't have value to the overall system, so we should give $0 or $0. Right? It doesn't provide value, so it just gives 0 value. So well, you probably know, like only there is one allocation rule that satisfies this the first four, which is the Shapley value. Surprise, surprise. But there is no other allocation rule satisfying that. Another one is individual rationality. We believe this is also an important property. It's like you are going to come here tomorrow with your electric vehicle, and you want to provide your data to the grid operator. So at least, I mean, I don't want to pay anything for making the overall process a bit more expensive. So it could be like my data is creating a negative effect in the overall operation. And this happened, and we have observed that. In other words, like Shapley value can be, for example, we don't want Shapley value to be negative, because negative value will mean I have to pay for that. You can think in the very, very beginning, first example, in the linear regression, every data point provides a value for the linear regression. If your point is an outlier, actually make things even worse. So this value will be negative. For example, if I use Shapley value, but I don't want to pay, so I share in my data. So it is not rational to me to have a negative value. So and this is a very complicated to satisfy in many allocation rules. And the last three, so this is existence and uniqueness. So most of many allocation rules actually satisfy that, especially if we have closed forms, and computational complexity. Okay. So this is in the book of William Thompson. Actually, he was listing more than 60 or 70 properties that we can find when we think about allocating value for that. So that is kind of a very, very reduced number of properties that we believe like it could be important. So let me start with some notion of individual contribution. So individual contribution is related with what one particular player, or in our case, one particular EV aggregator can provide. And there are two ways of understanding this individual contribution. It can be standalone. It's like I have my system, the grid. So I provided just only one player is providing the information, and this is the value which is generated. So I know like there's an increase of extra profit that we can compute like this. Or we can see this in the context of when everyone is sharing the value, and then I remove this particular EV aggregator from EV aggregator data from the blank condition. So this difference is related with this individual contribution in data science. Also, it is called leave one out. Yeah, when they want to understand what is the contribution of a particular feature, so they do a fitting. I don't have this element, and then this. So and then of course when we have this individual contribution, we are able to understand what is the rest of the value, and the rest of the value it is what is called non-separable contribution. So the idea of allocating cost or allocating value profits I think probably this is one of the first works. Maybe there are others that I'm missing. But this is from 1942. And so this is at the early stage of cooperative game theory field. And the idea was, it was in the context of allocating the cost of a project. Several projects, they are along a river. So you have different type of projects. And so how much will be the cost that every company has to pay for develop benefit that is created. But the idea is very simple. So we have these terms. So the allocation for a particular player or a particular target, it will be composed by two parts. One is the individual contribution, and the other part is some proportional non-separable contribution. And with this template, many authors have been proposing different type of allocation rules. Right? So, for example, yes, non-separable contribution is everything else. So we're summing up the individual contribution, and we have the total value of the process of the difference, what we can separate, and we just divide it among all the players. So when this non-separable contribution is equally shared from all the players, so just 1 over the number of players or the number of aggregators, it is typically called egalitarian non-individual contribution. Right? But this alpha can be something different, can be some proportional. So you can play with that, and you can have a lot of possible allocation rules. So the first one, I took this from literature. So it's from 1991, what is called a center of imputation set, and says like this individual part is a standalone value plus equal share of the everything else, this non-separable contribution. Okay. This has very nice properties in terms of complexity, because I need to evaluate the value function, this V, in the context of this two-step day-ahead market and the balancing market. One, for when everyone is sharing a value, and also n times. Right? So this is the complexity is approximately the order of the number of players that I have. Another allocation group that we use here is what's called equal allocation of non-separable contribution for Modi. And we have the same structure. So we have a part related with the individual contribution. In this case, related with the grand coalition. Just leaving this element out of the grand coalition. This is what's called marginal contribution in the grand coalition. And the rest is everything else we have not allocated. We divide it equally among all the players. Okay. Again, this is very nice in terms of complexity, because it has an order of complexity of n, being n the number of players that we have. Here is a summary table where we have like what you see here, Shapley value satisfying efficiency, symmetry, linearity, and non-player properties. In some cases, if we have complex games, but it's not always the case, we can also satisfy the rationality, satisfy existence, and also uniqueness. But the complexity, we need something exponential, so it's the order of 2 to the n. So when we have about 20 players, it becomes almost impossible to compute Shapley value. Even this is the kind of the gold standard. So this is the two other not very well known or less known as Shapley value, but this is the two other ones, because both of them they satisfy also efficiency, symmetry, linearity, but they are not satisfying the player. So we may have free riders that they get value. So they are not providing any value, but they can get some benefits, some payments for that, for providing data. But they are okay in terms of complexity. And because both of them, they are linear, so if we can make a linear convex combination of two allocation rules, they satisfy linearity, it will also satisfy the linearity and the same properties. So we come up with this one. I don't know if this is in somewhere, but just let's make half of the series and half of the years. I will show you how this time. And this is other ones that this is related with a family of values. So I'm not going to. I can go later here. Okay. Any questions? So we yes.
N is probably.
Okay.
N is the participant.
N is the number of participants. Yes.
And for example, 10 million of cars.
Yeah. It could be 10 millions of cars. It could be in charging stations. So we have, let's say, all these IPU institutes is one particular player, and IPU is in charge of providing this information to the system operator. So maybe in the IPU you have 100 cars or maybe 20 cars, and so we started to envision this as a charging station or aggregators of electric vehicles. Yeah, this is impossible. Yeah, this is like even with 20, so it will be almost impossible. I will give you an order of magnitude of shuttling. I just remark this because one of the participants from MIT in this project in 2019 published a paper on data markets. So how we can organize a market for selling and buying data. And the solution for allocating the value of the genetic value of this market, it was through the Shapley value. In particular, there are approximations to compute Shapley value, some randomization Monte Carlo Shapley value. He was using that, but still, this can be, I will show this is even not a very good option, and this can be a good alternative, good proxy to allocate value. Yes.
Can you get to the previous slide? No, the previous is all image of system. Closed loop.
Oh, closed loop. Yes. This is. This one.
I think that due to uncertainty in the real-time situation,
Yes.
you can get negative feedback.
Yes.
In the zone.
Yes. It can happen. Because those are like the data points, we can think an outlier. So if someone is providing value, a data point which is an outlier to the system, to the operation of the system, it can actually.
Do you consider such situations when P is negative?
We now, yes, I will discuss a bit later about that. Some particular example, but we still don't know how to answer this question. One of the typical answers is like if you run this market in many days and many times, so in average you will have something positive because this is not negative, so in expectation. But in a particular moment, you may have some negative value. For example, this is kind of the standard answer that I can give. We don't know how to make think that the value is not negative because it could happen that the value is negative as well. So we have to think in other type of business models for this because the setup is like, yes, we have that. This is the best forecast that we have. There's uncertainty. We either use this forecast or we replace with true data. And when we are replacing with true data, we should be better off. But it's not always the case. Okay, yes, you can imagine that we can replace this context of our market by something else. Like we can think about healthcare, we can think any of those complex systems. The bottom. On the bottom. No, I will. It's you or
No, it's you.
Фокус должен быть на презентации, правильно? Что? Фокус.
Okay. Who was listening? It's going the other way around. Maybe I can have to.
You can ask me.
Ну да. Ну просто я не готовился. Понятно. Ну это деталь.
Yeah, okay, yeah, it's good. So let me try to explain these ideas in a illustrative case study. So we have run different types of styles of grids. So this is a distribution grid, very simple. This is just one line. We have here a substation where we the grid operator used to get energy from the substation. As we are going further and further, so we can have in the other extreme some small generator, a diesel generator, for example, that we can use in the case that we don't have enough capacity here, or connection with other grid, which is yeah. So the idea is that to have cheap electricity here in the substation, and if we want to use something local, a diesel generator will be expensive. So while I'm creating this synthetic example, just to understand if there is any locational effects. So does it matter to provide the same data in node number 2 or node number 4? So if you are closer to the substation, will be better or will be worse? Should we have this locational effect or not? So this is some data. So cost of the day ahead is 1. Here is 3. If we buy energy the day ahead, if we need to balance energy, so after we observe the real data, and then we have to balance. Typically, it's expensive, so you have to increase up. It's 2.5 instead of 1. We have to increase here. It's 5.5 instead of 3. But this is negative. We have to reduce because we are not producing energy that we used to have. This type of setup is very similar to the news vendor problem. Maybe you are familiar with this news vendor problem, that the guy who needs to purchase newspaper today, but then he doesn't know what is the demand tomorrow. So this is very similar, but we have here a grid. Okay, but the idea is like 1 is cheap, and here 4 is expensive. Okay, and EV 1, 2, and 3, so the 1 is closer to the cheap location. In this type of grid, okay. Yeah. So we run different type of analysis, where we say that we have 3 EV aggregators for this particular case, and we saw one in this case. And we model all these flow constraint, power flow constraint, this flow, it's a model. And we decided, well, let's assume like the forecast is equally underestimated. So this is one of the scenarios that we'll analyze. So I have a forecast from the grid operator, which is equally underestimated for 3 of the 3 EV aggregators. So it means like in terms of when they share data, in terms of accuracy, they are providing the same increase of accuracy because 3 of them, they are equally underestimated. And then we see like overestimating are also underestimation, but it's not equally underestimated. I will show you. Yes. Yeah. So I will analyze these 2 examples. So I assume like the true EV aggregator demand is just 1.15. This is just a illustrative number. The best when we say equally underestimated. So this is the best forecast that the grid operator have, their own tool of forecasting, and say, well, I will have the demand is 1. So the error of this is for all of them. So the error will be 0.05 for 3 of them. Okay. So in terms of absolute error, It's the same. So they provide the same improvement. We will see if they get the same value of the data. Okay. And in the case, and even under estimation, we assume that the closer EV charging station closer to the cheapest one, well, the best forecast one. As we go farther from the substation, the error starts to increase, right? And this is proportional. Okay. And then on top of that, what I'm going to do is just to scale down. Like I have a factor, which is called loading factor. So instead of having a 1.5, just multiply this by alpha. So 1.5 by alpha, alpha can go from 0.1 to 1. And this is the same for the best forecast. So what I want to mimic is a grid which is not congested, it's not stressed. So I have a very little number of electric vehicles, or a grid, the same grid with a lot of electric vehicles. Okay, so two types of issues can happen in a grid. Very simplified one. We can have voltage issues, like the voltage drop too much. So then we need to find a way to operate the grid, or we can have congestion issues, like the line is not big enough, so which is congested. Okay, next. Yes, this is kind of an example. I think we can skip this next. Yeah, next. Okay, so here is the fair outputs that I'm showing here. So remember, this is this case of 4-node 3 EV aggregators. The 3 EV aggregators are underestimated. And here I'm representing what is the loading factor. Right? Let me start with the bottom figure. So when the loading factor is very small, so the EV aggregators actually have not much electric vehicles in there. So the total savings are smaller. As we are increasing the loading, we can increase the savings by saving data. Okay, we assume that 3 EV aggregators are saving data. So as the system becomes stressed, so the value that we can generate is larger. That is something that we should expect. And if we look in the vertical, so we see here, for example, for a loading factor of 0.2, the EV aggregator 1, which is closer to the cheaper generator, should receive 30% of all these savings. This is in percentage. The EV aggregator number 2 is a little bit there, so a little bit more than 33, like 34, and this is 36, something like this. Okay, this is how we read this. So if we are going to 0, so everything becomes like 1/3, 33.33. Right, so like the value is very close. By the way, this is Shapley value. What I'm showing here is Shapley value. Okay, I can compute Shapley value when I have 3 players. So here is the interesting thing. 3 of them, they provide the same increase in accuracy. 3 of them, they provide 0.5 error in terms of accuracy, but 3 of them they have different business value. So they provide different value to the avoided cost that we will have. So you can see here, like we're changing the loading factor. This is one of the takeaway. So we have locational effects. It matters where the data is shared, even if they provide the same increase of value. The second thing is, like as you see, as we are moving in the loading factor, if the grid is more stressed, so the value of the EV1 EV aggregator, the data of this EV aggregator is less and less relevant. So it's better to have data from the EV aggregator. They are far from the cheapest node, because this one will have not much problems to get satisfied with the balance market. Okay, so this becoming like this, but then we observe what happened when this starts to increase is because we have congestion issues. Here, what happened is voltage issues, and then we observe from here there's congestion issues. So the grid become more and more stressed because we have more and more electric vehicle connected. So we observe this even the same location can have different allocation values. at different levels of loading.
David, sorry, so from load factor 0.4,
Yes.
can we treat this market like separate markets? Because it will be congestion on some line.
Yes.
So actually, for example, electrical one is playing alone on markets with cheap electricity, and the electricals 2 and 3 playing on market with high price of electricity.
Yeah.
Is it so? Can we somehow show this cut of congestion that the market as a line is congested somewhere?
We can see here from here, this line 1, 2 is congested in this case. And because we didn't have a good forecast, we have to purchase energy from the expensive generator. I don't know how to separate them because right now we have only one buyer of this data, which is the grid operator. We typically operate the grid as a whole.
But still we can show that electrical one give an input to the planning of cheap generator or left side, cheap side. And electricals 2 and 3, they give value to high price.
This
Probably it will make sense to show where is the congestion in this sense.
In this case, the congestion typically happens from here to there in line
Between
1 to 2.
So electrical one will be on one market, yes? Is it correct?
Yes,
And 2 and 3 will be on the other side.
it's a combination of both. Electrical will be satisfied. The problem with the power grid is like you put electrons in the grid and you don't know where they're coming from. Right?
Yeah, but still it turned out to be very important from our previous analysis that we need to forecast where will be, how the market will separate.
Yes.
Probably it will make sense in this analysis, try to understand, to predict the congestion.
Yes. I think I need to think about this, but I think so. Yes, this direction. There are some related problems, which is still open. Like for example, at the transmission level, who have to pay for the transmissions grid for the lines, and we would like to know how much we are using of this transmission grid. And it is not possible to determine. We only can do this when we can approximate the system as a linear system, so very close to an operating point, and then we can derive some sensitivity matrix. So it will depend. The operation is kind of close to 0.4, so we know we may have this sensitivity matrix to know how much is responsible of some congestion. But in this case, it's just one line. It would be easy when systems are messed. It will be a bit more complicated to determine. Yes.
Next year.
That's
Actually, you can try again because sometimes you are on lower side.
maybe I can do it. Okay, yes. Well, I have no color here, but this is basically representing when you have, this is very bad forecast for the grid operator. So the almost 25% of, no, 33%. So 1 was the true demand, 1.5 was the forecast, no, the other way around. So you can see the avoided cost, the value generated by using this data actually is pretty big. It's a big share, like 25%. In these cases, of course, can be changing depending on the loading factor. But what I want to show here is like instead of using Shapley value, if we use other allocation rules, they are not as complex in terms of computational complexity as a Shapley value. So we observe here like we have a very close value. So this is an empirical observation, but doesn't mean like it's the same. So maybe the next one, can you go to the next one?
Next one, yeah.
Yes. Yeah, this is an example Shapley value here is this box, those square boxes. These values and Ian's values, the two allocation rules that I presented before. So you see that, well, you can capture what is a locational effect. Like this is the first one. We typically get less than 1/3 of the value, the profit, extra profit that have been generated. And also we have this loading effect also captured with the other one. It's not the same of Shapley value because they have different analytical formula. We cannot expect to have the same. What we observe here, like this convex combination of this value plus Ian's value divided by 2.
Right.
Yeah, actually it's pretty close, and I think we haven't checked, but for 3 players, I think it's the same. I need just, this is not difficult to prove, but just to write down all the terms of.
David, but in this case, information from any electric vehicles makes sense. There is no free rider.
Yes.
And this is very important because all other rules are not protected from free riding. So it will be interesting to slightly modify the model in order to investigate if it will make sense to free ride. Probably somehow to input another one electric vehicle because this was the main borderline between these rules.
Yes.
All the simple rules are not free from this, right?
Yes. 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 That's something. I have another example of free rider. The next. So can you go the next? Yes.
Next, yeah.
Yeah, this is the second one, EV aggregator 2. As we increase the loading factor, the value of this data becomes more and more important.
Sorry,
This is me.
Sorry, and I know the answer between dots and squares. The main idea is that you are treating the value in one case of personal value, and another one grand coalition -1.
Yeah, one.
And for 3 players, actually weighted combination is exactly like Shapley value. It's just for this very case.
Yeah, it's only for 3 players.
Yeah, only for 3 players. Yeah.
So I have other examples for 4 players, not the case, but this allocation rule also allows you to capture location of
It will be quite close, but with increase of coalition, it may move for a number of players.
Yeah.
So this is exactly a joke with 3 players.
Yeah. Okay, next one. The same for 3 and next one. Yeah. Okay. So the second case study that or second scenario that we simulated is again the same grid, the same number of EV players. The only thing that we are going to change is the estimation of the grid operator on the loads of EV aggregators. So the estimation of the forecast of the EV aggregator from the grid operator that I can use is 1.5 for the first one, 1.25 for the second one, and 1 for the third one. So it means like for the third EV aggregator, the forecast of the grid operator is good. Actually, is the true demand that we'll observe. So this is Shapley value, and we can see like the allocated value for the third one, for the third EV is 0. It's a null player, it's a free rider, which is because if the third one is sharing the value of 1, will actually not improve the overall operation of this 2-step settlement market. Okay, this is a very classic from the standard Shapley value. And we see like the second one actually is a bit better. And the first one is the worst forecast that the grid operator has. So we see like the first one actually have, now remember the first one was below, but now we have even above, because the increase or the improvement in this forecast error is better when the first one actually is showing this data. Okay, so we can capture these effects of the increase in the forecast accuracy by then. So we have, this is the case, this is the same loading factor, and then we have probably some variation because we observe voltage issues in the grid or maybe congestion issues. So this is an example. Yes, the same example. Here is the previous one. The same example, but we have changed the forecast that the grid operator has. So we have one free rider. We have one which is a very bad forecast, and one which is okay, it's something in between. And we can capture this with Shapley value. Shapley value have these nice properties. Okay, we can go to the next. And then this is the interesting thing. So using the other alternative, like C's value, Ian's value, so actually they have very similar capture. Here we observe for Ian's value, so we have negative value as you mentioned. So the one which is sharing the third one when this guy is sharing value at 0.3 actually have allocated negative value. Okay? And this can happen. Even Shapley value can happen. So
we get money from the rider.
Yeah, in theory, this guy have to pay for providing this data. But this is kind of the open issues now that it is not addressed. There is some option which called absolute Shapley value. But when you do this absolute Shapley value, you are missing some of the properties, free rider property. So you can avoid to have negative value, which is this is not individual rational. Okay, we are not satisfying this property. Okay, but we can capture the same type of behavior. Okay, next. Okay, next. So here is about the scalability, the question that you mentioned before. So assuming like we have a system, a complex system, and we can run the operation of the system in 2 seconds. It's more or less what it takes a computer for solving one of very big, a few nodes. But let's assume that we have only we require 2 seconds. So if we have 4 players or 4 EV aggregators sharing data, for Shapley value, we require more or less 1 minute to compute, to simulate all these combination of day-ahead market and balancing market, and then compute Shapley value. Computing Shapley value is simple, but the complicated part is populating the value function vector. So we can use Monte Carlo Shapley value, assuming like 1,000 iterations for stopping criteria. In this case, well, for 4 players, doesn't have sense to use Monte Carlo Shapley value. But if we have like 10 aggregators, so Shapley now requires 1 hour for taking all the combination, 5 hours for Monte Carlo Shapley 1,000 iteration. So for the other 2 elements, so we are requiring like a few seconds, 1 minute for 10 players. So if we go like 1,000 aggregators, could be the size of maybe a city like Moscow. Thinking aggregators, not individual players. Yeah, Shapley values, of course, we forget about Shapley value with 100 aggregators. Even Monte Carlo actually can have some problems. And this, it could be okay, like 1 hour computational time could be more or less okay for this type of problems. Okay, this is just to have an order of magnitude. And I think that that's okay. Next, I will conclude here. Yes, next. Okay, so I have plenty of examples in the backup if you want to see more examples or more things, but I probably finished with more questions than answers. I try to motivate that the data that can be generated from EVs, electric vehicles, or maybe other data points in a different particular context can actually have some value. We started to try to provide some framework for quantifying the value of this data and to allocating value of the data for every layer or data point. So this is what we have been presenting here. We believe many of the improvements in the fusion in power system will not be coming from technology, because we have plenty of technology ready, but will be coming from algorithms. Remember at the very beginning, the Tesla have developed this auto bidder, which is just a software to do trading with the batteries. So many of the improvement in future will come with algorithms, and algorithms need data. So this is what kind of our big picture of this project. And we see data can be an asset, can create an added value to this chain of value that we can get from electric vehicles. And the next one. Yeah, so some of the conclusions that we observed from this particular sample, we see there are locational effects, especially they are related with losses, congestion, voltage issues. There are alternatives to Shapley value that they are a good proxy to Shapley value. They are not Shapley value. Still, Shapley value or other alternatives can actually provide negative values, even doesn't have solve the free rider. But I don't think that we can solve that. We have to decide what are the properties we want to satisfy, because cooperative game theory have already looked into this problem pretty much from the axiomatic point of view. And we already know that there are only a few allocation rules that can satisfy these particular properties. So we have to decide what are the properties that we want to select. It's kind of a menu. So we want these properties. So we have these options for and yeah, and that's so we're still thinking about different type of business models, how we can coordinate. But that's all. That is all my presentation for today. I hope I haven't extended too much.